All right, let's look at today's Check Your Understanding. So it says, according to the American Dental Association, 8% of adults have never had a cavity. So right here, we see we've got some form of a claim. This is going to be our P. A dental graduate student contacts a simple random sample of 1,000 adults. So this is our N. Okay, and calculates the proportion P hat in the sample who have never had a cavity. Part A asks us to identify the mean of the sampling distribution of P hat. So we need the mean of P hat, which we learned today was equal to P, and P is 8%, so my answer should be 0.08. Part B asks us to calculate and interpret the standard deviation of the sampling distribution of P hat. Check that the 10% condition is met. So I'm looking for the standard deviation of the sampling distribution of P hat, and I know that's equal to the square root of P times 1 minus P divided by N. Okay, and this is all underneath that square root. So plugging in my values, I get the square root of 0.08 times 1 minus 0.08, so 0.92 divided by my sample size, which was 1,000. And when I put that all in my calculator, I should get 0.009. And then it does ask us specifically to check the 10% condition. So I'm looking to see that my sample size, 1,000, is that less than 10% of the population, which would be all American adults. And I'm being specific with the American because we're looking specifically from the American Dental Association. Adults. So yes, 1,000 is definitely less than 10% of all American adults. And then we need to interpret our standard deviation. So I can say that the sample proportion of adults that have never had a cavity typically varies by 0.009 from the true proportion of 0.08. So how is this different from the interpretation of standard deviation that we've looked at before? Well, we see that we still have our keyword of typically varies, okay? But instead of typically varying from the mean, now we're saying we're typically varying from the true proportion. So just kind of the difference between those that we've seen before. Okay, part C, is the sampling distribution of P hat approximately normal? Okay, and in order to determine that, we need to meet the large counts condition. So the large counts condition says N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. So my sample size was 1,000 times my proportion 0.08, and that is equal to 80, which is in fact greater than or equal to 10. And then our other side of it, 1,000 times 1 minus 0.08, or 0.92, and I get 920, which is definitely greater than or equal to 10. So because both of those are greater than or equal to 10, we can say that the sampling distribution of p hat is approximately normal. Which is going to help us in the next piece of this problem. In part D, we're asked to find the probability that the random sample of 1,000 adults will give a result within 2 percentage points of the true value. Okay. So our true value is 0.08. So within 2 percentage points, 2 percentage points below would be 0.06, and 2 percentage points above would be 0.10. So since I know I have an approximately normal distribution, I can draw my normal curve. The mean we said was 0.08 with the standard deviation of 0.009. And I want to know the probability of being within 2 percentage points. So between 0.06 and 0.10. So I'm looking for this probability, this area here. Okay. In order to do that, I have to have a standardized curve so that I can use table A to get, or my calculator to get the results. So if I'm converting to a z-score, remember z is equal to the value minus the mean divided by the standard deviation. Okay. We talked in class today how we can put in p hat minus p divided by the standard deviation, which is p times 1 minus p divided by n, and that'll get me my z-score. So I can do 0.06 minus 0.08 divided by 0.009, and that gets me negative 2.22. If I did this with 0.10, I would get a positive 0.22. So I have two z-scores. I have z being positive 2.22. And again, that's if I plugged 0.10 in. And then I also have negative 2.22. Going to table A. In table A, I'm going to go to negative 2.22, and I get 0.0132. So this one is 0.0132 is the probability of this area here. Okay. For my upper area, again, when I go back to table A, I should get 0.9868. Okay. That is this entire red area. Okay. And so in order to get just the blue area, I'm going to subtract those two numbers, 0.9868 minus 0.0132. And that gives me 0.9736 as my probability. Okay. So that's if you're doing it by hand. If you want to do it in your calculator, the command that you need to use is normal CDF. Okay. And you can find that by hitting second bars, and it's right one of the first values. And then I need to put my lower bound, and that's going to be my lower number that I'm interested in, 0.06. My upper bound which is my higher number of 0.10. And then my mean was 0.08. And then I also have to include my standard deviation, which was 0.009. And you'll find when you put it in the calculator that you get the same value here. So we've got a 0.9736 chance of getting a result within 2 percentage points of the true mean. Part E, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? So just like we talked about in our previous lesson, the bigger the sample size, the less variability we have. So the distribution, as far as the shape goes, the distribution would remain approximately normal. But the standard deviation would decrease to 1/3 of the value. And the mean stays the same. How do I know that the standard deviation is decreasing by 1/3? If I take my proportion, 0.08 times 1 minus the proportion, 0.92, and I divide by 9,000, that gives me 0.003, which is 1/3 of my standard deviation that I had before, the 0.009. If you just said it decreased, I personally would count it correct. AP graders, of course, are more harsh. All right, if you have more questions on this, which you might, make sure you ask them in class.